Have you ever noticed anything strange about how commercial jets land? It looks like right before they touch the runway, the pilot has to angle up just a little bit. There's no way that these experienced pilots are coming in so hot that they have to pull up to save their passengers a firm introduction to the back of the adjacent seat. This counterintuitive touchdown maneuver, called landing flare, is actually an elegant solution to a phenomenon faced by pilots worldwide: the ground effect. You see, this is a perfect example of why you don't let engineers name things. They will give it the most unimaginative, pragmatic title they can possibly manage. And so, the ground effect is an effect caused by flying near the ground. Commonly, the ground effect is described as a cushion of air and gives a plane mid-takeoff or mid-landing the experience of increased lift and greater efficiency. The motion of planes can be simplified down to 4 forces: weight, thrust, lift, and drag. Weight tries to pull the plane down, so lift steps in and says, "Hey, why don't you try not doing that?" So weight's all like, "How do you plan to stop me?" Then lift whips out a couple of CFM56s and all like, "Yeah, I don't know, with like 60,000 pounds of force." And weight's all like, "Yo, my buddy Drag's gonna fight you." Psh, whatever, says lift. I just smack some big freaking metal plates on the side and boom! That's how you get the Boeing 737. There are 2 predominant explanations for the ground effect out there, and they both likely play a role. The first involves the deformation of wingtip vortices. Making up about 50 to 60% of the resistance experienced by a plane, induced drag is given by this equation. Quite simply here, you can see that the coefficient of induced drag is given by the square of the lift coefficient divided by pi times the square of the effective wing length over the planform area of the wing. As the plane flies, vortexes trail out from behind the aircraft. In normal high-altitude flight, those vortexes roughly extend from the fuselage to the tip of the wing. Everything's normal, we're all good. Enter ground. The vortices now face an obstacle. The lower portions get redirected sideways, and this causes them to be squished out beyond the tip of the wing, increasing the effective wingspan. If we look back at that fun equation for the induced drag coefficient, we see that as wing length gets longer, the drag coefficient gets smaller. Less drag means the engine can achieve greater thrust for the same fuel efficiency. The greater thrust experience without touching the throttle of the plane can give pilots the experience of floating. This gives us an insight as to why pilots pull up as they approach the tarmac. By steepening their angle of attack, they can use the increased drag to balance out the excess lift. This technique was most evident in the out-of-service American Concorde. Due to the supersonic accommodating wing geometry, the problem of the ground effect was exacerbated, requiring the landing flare to be so significant that the nose of the craft was designed to droop on approach so that operators could actually see the runway. The second explanation involves the interaction of downwash and, you guessed it, the ground. In normal flight, downwash flows off the back of the wing due to the Coanda effect, generally in a downward direction. It is this redirection of mass that contributes to the wing's lift. Once the plane approaches the ground, however, the downwash cannot just flow freely. The air between the wing and the ground is compressed, creating a region of high pressure. The pressure gradient that is then formed across the wing is greater than what is normal at high altitude flight, providing the plane with greater lift. Okay, well now that we have an understanding of how it works, what is it good for? Well, to start off with, it's been utilized by hobbyists such as Daniel Riley to build his RC Flying Sled. Riley constructed the prototype of his Flying Sled in 2009, which was capable of skating across the snowbanks and then launching itself into the air. Fast forward 6 years and Riley returns to the idea. After building and successfully operating 2 improved models, he notices that sometimes when the sleds had significant speed near the ground, they appeared to momentarily hover. He recognizes this as the ground effect, and later in 2015 reinvents the sled to fully exploit the phenomenon. By adding wings to the side, Riley grants the sled the ability to drift gracefully above the surface of the snow. Notice that you can hear the motor working harder when Riley flies the sled above its hovering altitude, and then idles back down when it returns. When the sled exits the ground effect, the surplus lift is no longer present, and thus the motor goes into overdrive in an attempt to maintain the same amount of lift. While a hovering sled is certainly impressive, Riley is not the first to take advantage of the ground effect. On August 11, 1985, a U.S. reconnaissance satellite captured this image. It was our first glimpse at Rostislav Alexiev's Ekranoplan. This insane machine was nicknamed the Caspian Sea Monster, as it could achieve takeoff with a maximum weight of 830,000 pounds, reaching a top speed of 342 miles an hour. Now, there is some debate as to whether or not this feat of Soviet engineering should even be classified as a plane. Naked Science reports that the International Maritime Organization classifies the Ekranoplan as a maritime ship. Now, unfortunately, I could not find any verification of this statement anywhere, but it certainly seems reasonable. I mean, look at the thing! It's bigger than those buildings! Flashback to present-day Japan, where Yasuaki Kohama is attempting to solve two of modern society's biggest needs: an environmentally responsible transportation system, and one that is high speed. His answer? The AeroTrain. He and his team are developing an aerodynamically levitated train by taking advantage of the ground effect. Analysis of successful prototypes has shown that the AeroTrain experiences less wind drag than magnetically levitated trains, which is another proposed solution to high-speed travel. Operating in a U-shaped guideway, the AeroTrain does not suffer from the safety hazards that plague ground effect vehicles that operate over water. Also, the uniformity of the track allows for the additional lift to be precisely manipulated, and thus used most efficiently. Its vertical guide wings also use the ground effect to repel the AeroTrain from the sides of the guideway, keeping the vehicle on a straight course.